now I'd like to invite Dr. Gergely Szalay from Laboratory of 3D Functional Network and Dendritic Imaging Institute of Experimental Medicine, Hungary. So he is presenting on the title Interfering Dendritic and Cortical Neuronal Assemblies During Visual Learning Revealed with 3D Random Access Microscopy. So welcome to you.
Thanks for the opportunity. Welcome everyone, even online. So what I like to show you today is about the patterned optical stimulation, and although we can do nice stuff there, like whatever carve different shapes, that's a homogeneous sample. For now, we're gonna use it for it will be differently, and we so we're gonna jump again a different field, and we go to biology and biological neuroscience. And I want to introduce this all optical integration phrase that we use in this field. That basically means that we have our volunteers, so we're working in vivo mice. They're performing a behavior task, and we are able to capture what the neurons are doing in their skull. During that time, we try to find the neuronal ensemble that's coding the certain perception we are seeing, and then on the next step, we try to stimulate back that pattern and see if that have any behavior effect. This is much easier than said and done. For that screen, so for the calcium imaging, we have a very nice tool. It's not developed by us, but we also improved on that. So now we can introduce different calcium sensors in the brain, and as we've seen in the video, we make the activity visible. We can detect that with a microscope, and also for the ensemble detection, there is certain tools or certain libraries you can download from GitHub, which is try to find certain neuronal groups that are fired together more reliably than other cells. That's also, let's say, that's done, but all the others, it's still a challenge. And the principle of why it's challenging, because if you imagine both the behaviors, so we have a small mice that try to perform a visual task, which is not the perfect, not the favorite modality of the mice, and also the neuronal activity, even if the mouse behaving the same and see the same structure, the neuronal code of that is always different. So basically, we try to find the correlation between two very noisy signals. So what I'm going to show you, that's we try to improve on that. So basically, the challenge is I turn them to goals. So that's what I explained to you. So this is the very same trial. The mouse performed more than 200 times. As you see, the average neuronal activity is quite reliable, so you can see the response for the different part of the signal. Actually, it was a long stimulation, but if you look at the individual traces, they are very noisy and very different, and there are some traces there is not even response. So what we try to do, and what I'm going to show you so this is the intrinsic property of the neurons in that cortical region, so we can't really improve on that. What we can do, we measure as many neurons we have, and from the population code, you get much reliable answers than from a single cell. And also the learning is not so good. So that's the spring session. It's actually from my measurement. So we need quite a lot of training days for the mouse to be expert and still doing some errors. That is just jumping back in the performance, as you can see. So we design a new VR environment tool, and the behavior make it more reliable. And the third one is when you get if these are working, when you try to re-stimulate this pattern, that the state-of-art technology is using a holographic scanning, so spatial light modulator, and with that the program that we have one single LED to illuminate all the cells. So if you have more cells, then less pixel for one cell. And if you try to code one spatial location with less pixels, the resolution starts to decrease. And instead of single cells, you like stimulate these very large spots. So we're gonna do it with a different scanning mode. So going to the first one, can we turn off that? So how we increase the number of cells measured. So usually if people like want to record this kind of activity, what they do, it's like, I forgot to mention, this is two-photon microscopy. So we always have to scan with one. So it's a laser scanning microscope. You have one point of scanning. So what you can do is that you scan the whole field multiple times. That's not super fast, especially if you have multiple layers. It's in the range of like less than a hertz. So the idea is that, okay, then target only the points we are interested in, and we can go much faster that way. So, and it's kind of a trade-off. So you can measure points and you decide that you like spend more time on an interesting point with so increase this, the signal to noise ratio or measure more cells. But overall, you have like a couple-fold increase either in the speed or the signal to noise ratio. And how we do that? That's the skeleton or the drawing of our microscope. We won't tell all the details, but the heart of all the stuff, or all the stuff, is these acoustopical crystals. These are special dielectric crystals, and the property of those that if you generate like a mechanical wave in the crystal, that's the wave is like literally like pushing together the material. So the refractive grating is generated, and depending on the frequency of the sound, you can reflect the light more or less. So that's how you scan in a point in X and Y. And if you use it like a curved or a nonlinear grating, then you can even focus. And that's how we go in different Z directions. So you can scan the multiple points in the plane. And the good part is that you only have to wait as long as this mechanical wave goes through the crystal, which is 30 microsecond. And in the next 30 microsecond, you can decide that you use a completely different wave and jump in a completely different point in the 3D volume. So yeah, so how we use it in practice. So first we of course measure the whole volume just to see where are the neurons. It can go down like around 700 micrometers, so we can see through the whole cortex, this for the mice. And for the measurement, we only select the points we're interested. And by limiting the measurement to the points, it can be much faster. So that's kind of a live image. So like different links and size shows the activity of so every point is put down on the cell body. Moving forward. So that's so far so good, but what we want to go for living mice. So if the mice behave and there, then of course you start to move. So if you measure only at a single point, then the movement can like ruin your signal. So that's like, of course, that's the worst case example, but if you try to measure very small particles, they are dendritic inputs. So that's the input side of the cell. Try to measure those, that movement can be so large that you lose the signal so that it can't really like compensate for that. So what we came up for so that's the crystal in working. So I said that's the chirping grating can focus the light. But if we just misalign this grating a very little bit, then we can let this focus point to like go or drift along a single line. That drift can be like any direction in space. So you can organize it to be along the cells. So you can like design all these small like volume elements or surface elements along the process you want to measure. So let's say that's an example for that. So the measurement region, like it's spreading along the dendritic segment for this example. So the video we capture for this measurement could look like that. So this is the raw image we captured. And for now, you have like, even if there is motion, you have enough spatial information to compensate for this motion. So we are handling this as a video and you can motion correct for that. And this is the final result. So like the neurons are stable enough to capture the activity from the dendrites. And of course, depending on the measurement, so how much movement you have or which part of the neuron you're interested in, you can define different segments. So yeah, it can be even more than that. That's what they are suggesting, and that's what the software supporting. I won't explain all of these just for the sake of time. The chessboard scanning, when you have the small areas along the neurons, that's what we use the most often for network measurement, because then you have all the cells. So you see the output of the cells, the cell bodies, see them blinking, but you still have some spatial information to motion correct. So that's the raw video, and this is after motion correction, and this is the captured activity. So that's what the mouse sees is some different rating, and that's what the brain doing in the meantime. Yeah, the multi-layer measurement is just if you need to measure the dendrite as well, so you can capture this kind of videos, which is cool. So the activity is color coded. So, and if you're not interested in the postsynaptic or the presynaptic, you want to measure the inputs. How we usually do it, that so we put these lines along every dendritic input, because if the surgery is fine enough, then usually the movement is limited to one single axis. That is one example. My guess is that usually you can make a very good surgery, very tight to the skull, but feel the brain moving inside the skull because there is some vessel there which is pushing that, but it's usually pushing in one direction, so the movement going one direction. So if the direction is matched the direction of your line, even if the line is moving, or even if the point is moving, you still measure what's happened. So that's the improvement. So this is with a single point, and this is with the line. So we can improve to the quality where we can detect the activity at least. Yes. So that's how we measure. And going to what we measure. So I mentioned that we improved on the behavior device as well. So our claim or our original idea was that usually the problem with the usual behavior system, that we try to train the mouse that it's seeing the monitor whatever goes to the mouse, but the mouse have a very large visual field that's basically more than, so it's 190 degrees, so it's seeing something behind and up to the sky. So the monitor is covering a very small part of the visual field. So we try to cover. So we try to cover it so no other stuff can take its attention. So we do it with these small VR goggles. We done an optical model, so we try to design a lens that or filling out most of the visual field of the mice. So this is on the small segment we don't viewing, and the mouse performing. So it's moving in a virtual reality. It's running in a small wheel, and as it's moving, we move it in a virtual reality system. So here we just tested that how well the mouse feels it's real. So it was an untrained mouse in just a linear corridor, which ended up with an abbey, and we wanted to see if the mouse stops at the cliff or at the edge. And the red curve. So this is time trigger to the point when it's reaching the edge. So the red curve is with this oculus. That's how we call this mouse oculus, and the blue is with the normal monitor. So it's much often stopped at that point. We measured it with 1 and 2, and to do a monitor covering more than a single monitor, but it was always better with the oculus. Okay, and the third technology I wanted to talk about. So now we have a mouse that's doing some behavior. We can measure what's the neural star. And the next is that one back the activity.
So sorry. Sorry.
So what we do, again, I won't talk much about the molecular biology, but we can have another sensor where with one laser we measure the cell and simulate with others. We have the two lasers at the input side of the microscope, and by change, so I show you this equation before. So it's the diffraction is strongly dependent on the wavelength. So if you change the center frequency, it's either optimal for one wavelength or the other. So one is going through the system and the other is just like somewhere like hitting the wall. So you can change in that 30 microsecond, not just between the points and amplitude, but it will also change the laser line. So change between stimulation and measurement. Yeah, this is how where the other points going. So the blue is the field of view, so that's only one point is going there. So that's just the very first measurement we have. We stimulate at this thread point with a very short stimulation, and we see the activity rising. The delay was like 6 milliseconds. 6 milliseconds on average, maybe 8. Next, I don't know, it's not much neuroscientist in the room, but the question was here that so there is this 30 millisecond number, which is basically the time that the input should arrive to the brain at the same time to be considered as one single event. So I wanted to check that how many neurons we can stimulate in that time. So yeah, I started with 100 and checked how many is within that window, which was like 90%. So basically 90 cells can be stimulated together like in the same event. And of course you can have much more cell, but then the space, the temporal dynamics is a bit misaligned. So here I had half a second to stimulate that many cells. Okay, so that was the technique, and okay, let's try it in practice. So I can do that. Okay, so we have these devices we already discussed one time in this Weaver protocol. That was this virtual corridor. The mouse was going this corridor, and it's either teleported to another, so like a control, like a teach zone, or where this have it's have to escape from them to avoid the aversive stimuli and have the control zones, and we can compare the speed and the neuronal activity. So what we see that after a couple of days of training, the mouse was like, this is the neuronal responses for the given zone, for the aversive zone, was much different than from the control zone. And that's the interesting part. Maybe go here. So basically, like what's the new and why this? So what's the advantage of this Weaver device? That as the mouse have the full immersion, it's learning much faster than before. So it's not just, as I showed in the previous example, like after 3 weeks of training, we check how the already developed brain activity looks like, but we can see what's happening on the real time. And in 40 minutes, the mouse is able to learn the task, and we see how the network is changing in that short time. And basically, that's what's the most interesting, at least for us. That's here the red is the amplitude for the aversive zone, and the gray is for the control zone. And what we see that, like in the first, let's say half an hour, like both representations start to increase. So the mouse, it's being like receiving the aversive shock, and it's trying to find out what's happening and increasing the brain activity to be able to like form the connections to learn or understand what's happening. But at this point, finally it's understood, and it's know that the representation of the aversive zone is important because I have to escape, and the representation of the other zone is trying to or starting to decrease. And these representations actually, that's the amplitude, but also the two network was also spatially different. So different neurons were holding or like coding this information. And okay, so and the next question of how to stimulate back. So basically, we want to stimulate these red cells with this activity. So the question is, okay, that's the activity I want to reproduce, but how I drive the laser to do that? Because it's not like what's the amplitude you put into the tissue is different of how you stimulate. Being made an okay, so that's the equation where I usually lost my the audience, but I tried to explain it, or I transfer it from more different way. So I want to reproduce the responses, and I can drive the laser like at every time point separately. And I have the G function. That's basically how, if I have a single cell, the activation of that single cell or the amplitude put in the single cell defining the activity. Maybe if I move on, it's really more clear. The first part was just the temporal part. So as I can like drive continuous signals, I just measured that if two events is separated by 200 milliseconds, that's basically like for the emerging together. So I use 200 millisecond bins. Then the G part is how, if I have a single cell, how the amplitude applied on that cell defining the activity. I've seen this, so this is the laser intensity and activation, and know that this is the log scale, so it's not a linear like correlation, but at least it's something that can be written down in a closed function. So they have a threshold, a logging phase, and the saturation phase. Then the next question, okay, that was one cell, but if I have multiple cells in the network, then if I stimulate, let's say, this cell, it's also having activity on all the other cells. So like altogether, if I just use this G function on all the cells, then the altogether activity would be larger because the cells also signaling to each other. So to test that, what I did, so I had, I think in that case, like a bit more than 100 cells. I just keep measuring all the cells and one by one stimulated the cells after each other. And that's the connection matrix I get. And what I like here, that know the symmetry in this matrix, but it's not something that something that the measurement is dictated, because like when I stimulate cell 90 and measure cell 20, it's a completely different measurement and a completely different time point when it's the vice versa, so stimulating cell 20 and measuring cell 90, but still it's like a symmetric equation. And yeah, that's the, actually, if you, in that format, that's precisely that matrix there. So I measure that, and like noting the symmetry again, it's not just that cell receive activity, but also the cell receiving activity for multiple cells that are stimulated. So how I measured that, I like picked one random cell, see how it responded to an activity, and then picked one other cell and see if I stimulate that to how the first is responding and others is how the first responding. And I see this curve, which is like a nonlinear, and but again something that can be written down with a closed form. That's this equation. So having all this, I can solve the full equation and test how I can replay the activity. So here the red curves were the template basically, so what I wanted to stimulate, and the gray curves are how close I get to that. And so actually, like at every panel there is 10 gray curves, but they are like so overlapping that it's hard to see. So like at least by itself, it's very reliable, and it's like at least it's like catching most of the features of the original activity. And yeah, that's how we are right now. And actually, we are like testing how the back stimulation is affecting the behavior, but I don't have that result yet. So or I not as clearly formed that I wanted to present here, but they are like at least promising, but not perfect. But anyway, like in like a summary, that we show that we can measure a large set of neurons with a millisecond temporal resolution. We can restimulate them, and the mouse virtuality provide the fast and robust learning. And what's the next part? So what I tried to explain in the previous minute, that we're working on the back stimulation, but it seems like that it's not only we have to understand how the brain is working, but as to remember this developing REM activity, also the brain is changing through the activity. So it's partly we are learning how the brain is working, and partly the brain is learning how we try to stimulate it. So that's why it's still a challenging part, but that's for the future or for the next conference. And by that, thank you for the attention, and thanks everyone who collaborated in this work. And part of that advertisement, we are looking for postdocs. I don't know who's listening for that, but we are moving to this nice to the it's actually nice.
A great parameter and an instrument to evaluate a normal mouse. But what about a diseased mice and induce a disease in a mouse, and to evaluate the effect of the change? I applied acupuncture, and I'm very amazed. The achievement beyond my expectations. What about having such a
So like, as I use the word device, so it's basically the device that we offer that you can measure, let's say there were like 300 neurons with what we have coupled at the first resolution. And what to use for that is, of course, it can be different. So we use the training because we try to, I mean, the final goal of our lab is visual restoration, which like in the retina it's working better, but of course in the cortex on the understanding phase, and that's see what if you have different disease, then of course if you have a good model, then it's working. The bigger problem so for blindness, it's easy because it's very easy to generate blind mice. Actually, people using transgenic mice not to be blind, but in like for Alzheimer, I don't know how precise the model, for example, because they like in different molecular species than on humans. So it's always the question of how reliable models you can find, but otherwise, if you have the model to measure the neurons, this device can do, but yes, still a device. So the model is
when it will be applicable, we can request you to measure what we are doing, evaluate the neurons, and maybe it's applicable for us to share with you.
Yeah, we should discuss that. It's always disappearing like that. Sure. That's it. Thank you.
Maybe I'll just contact the people from the staff. We have some questions from the online participants as well.
Okay.
So it's from Shirsha, and she is asking that what are spatiotemporal aspects? What is a spatial cluster?
Yeah, okay, so spatial cluster can so basically what we are doing, like for starter, we just have the mouse behaving. Yeah. So actually
Not working.
no, it's not. That's it. So okay. So what we are doing, so basically when the mouse is behaving, we just, for start, we don't really like try to make an assumption, just measure as many neurons we have. So like in this case, even more than 100, so a couple hundreds of neurons. And then we have the neuronal activity and have the behavior tract and try to find so that what we call an ensemble is a set of neurons that like more likely fire together than just the rest of the neurons. So that's for this cluster. So that's the cluster of the activity, and the red line is the chance level. So we just shuffle everything, and that's the randomness of something firing together. And like when it goes over, then we find this in a co-activation. So we have the points of co-activation, and then we try to see that what was happening at that time. And basically the ensemble or the cluster is like vice versa. So when we find this cluster, then we check that how those cells were distributed in the space and what was the activity pattern.
Yes, please. Yeah. Okay. Thank you for your time. So thank you so much, sir.